Welcome back everyone in the third video of this 11AX series. Today we are going to talk about the phi layer enhancements in 11AX. So we will discuss the usage of the long OFDM symbol. Basically, a standard Wi-Fi symbol duration equals the IFFT symbol duration added to the guard interval. So we have 3.2 microsecond as our IFFT symbol. Adding to that either a long guard interval or a short guard interval, we can come up with 4 microsecond or 3.6 microsecond. That was prior 11AX. Now in 11AX, we actually use different numbers. So for example, the IFFT symbol equals 4 times the symbol duration used in 11AC. Same case for the guard interval. The guard interval of 400 nanosecond was removed. So the first guard interval starts from 800 nanoseconds used in 11AX. They removed it because the usage of 11AX was mainly to enhance the throughput in outdoor environments. And actually, 400 nanosecond is something insufficient for outdoor operations. Okay, so it is actually good to learn and memorize these numbers, but why are we looking into these things at this time? The idea is we would like to understand how moving from this OFDM symbol duration into a longer one have helped to enhance the Wi-Fi operation at the physical layer. Okay, so now we have a question. I need to say the question and we have to contemplate about it and provide an answer. So the question is, how does the usage of longer OFDM symbol help enhance the 11AX operation at the phi layer? So in order to answer such a question, we need to get back in time in the college days and revisit the wireless communication principles. We used to study about a function called FFT, which is fast Fourier transform, and also IFFT, which is the inverse fast Fourier transform. So basically, if I have a function of time and I apply IFFT to that function, okay, then I will get the function representation in frequency domain. Let's have a look at this function. Let's assume we have this function in time domain with amplitude of 4. So this one is plotted as f of t over time. Now, if I want to get the function representation in frequency domain, I should actually apply this to FFT function, and we will get, let's say, a different plot for the same function but in a frequency domain. Let's say we got actually a discrete representation of the function. Just for example, this is not accurate, but just we need to understand the idea, not the exact representation of each functions between time domain and frequency domain. Let's say we got this. Okay, this is f of f, the frequency over frequency. Okay, and let's take the amplitude in frequency domain. Let's assume, just roughly speaking, that it equals 2. By the way, if if I apply the IFFT in the reverse direction from frequency domain to the time domain, I can also get the time domain representation of the same function. Okay, now why do we study that? Because actually we want to understand how this helped in the phi layer enhancements of the A2.11ax. There is a principle we studied in the university, and it says if I apply a change in time domain, okay, if I apply a change to a function in time domain, then there should be another form of change applied to the function in frequency domain as a result of applying that in time domain. And by the way, if we also apply the same function in frequency domain, we will have a change or another form of change applied to the function in time domain. So let's take what applies to our case from this principle. If I make an expansion to a function in time domain, then in frequency domain, I will have a compression. So the inverse of that function. So let's get to the time domain. If I want to multiply this function by 2, then the amplitude would change to 8. In the frequency domain, the change would be the inverse of this change. So basically, instead of multiplying by 2, I will multiply by half, 1 over 2. So the amplitude or the frequency reading in the y-axis would be equal 1. So the key takeaway from what I have explained here is that if I do a change in time domain, then there will be another effect that we can see in the frequency domain for the same function. And we agreed that we will focus on the expansion and compression. Good. Let's clear things. So in 11AC, in time domain, we used to use 3.2 microsecond as the IFFT symbol duration. Now we moved from this number to this number in time domain, so we applied it by 4. So in frequency domain, how does that react? So in frequency domain, just for the sake of explaining that, let's take, let's say, a small part of the frequency domain that represents the subcarriers used in 11AC, let's say a frequency resource. We have the first data subcarrier, the second one, the third, and the fourth. And the subcarrier spacing equal in frequency 3, 1, 2.5 kilohertz. Okay? So now going into 11AX, the subcarrier spacing actually has changed. Why? It has been changed from this number to this number. That actually depends on the change that was done in the time domain. So here we multiplied by 4. At the frequency domain, we will divide this number by 4. So dividing that by 4 would exactly equal to 78125 kilohertz. Okay, so up until this point, we have learned a lot about the changes between time domain and frequency domain, but we still didn't reach to the point that explains to us how does this change enhance Wi-Fi at the PHY layer. Well, now I can tell you the answer to this question is easy, because as you can see, if I have this data subcarrier, by this compression that we made in the frequency domain, we can insert other data subcarriers in this space. So instead of having one data subcarriers, I can replace those in 11AC by 4. So having, let's say, extra subcarriers used to transmit data will result in getting higher, let's say, data transfer rate, and thus will enhance the overall throughput for 11AX transmissions. So that is the final answer. We actually reviewed everything related to FFT and IFFT and frequency domain to time domain conversion and vice versa in order to understand this point. So the synopsis here is increasing the OFDM symbol actually decreases the subcarrier spacing and thus increase the number of subcarriers that will be used in order to transmit data. Okay, so I hope I explained it in a good way that you can understand. I know it took time to explain this, but I hope you got it in the right way. Let's clear the screen and move to the next section. Okay, now we are going to talk about subchannelization, and actually it refers to the ability of dividing the RF channel assigned to the access point into smaller subchannels, or they are called RUs, resource units, where instead of assigning one channel to one STA at a time to transmit or receive data, then I can get these smaller chunks of frequencies and assign them to multiple stations, which will allow them to actually transmit or receive concurrently. This is an extreme enhancement in 11AX because it will help cut down the contention within the Wi-Fi cell. Before we get into that and how it helps exactly to enhance the 11AX operation in the PHY layer, let's have a look at the 20 megahertz channel. So basically, as you can see, this is, let me grab my pen and I would take this color. Okay, so basically this is the original channel. Okay, I think I picked a bad color. Okay, so this is the original channel. I can divide that into the following options. I can divide it into 1, 2, 3, 4, 5, 6, 7, 8, and these two also could be considered an RU. So what is an RU? It is, let's say, a kind of a group or a grouping of frequency subcarriers together to form a resource unit. So this resource unit contains 26 subcarriers, same case for the others. You cannot, let's say, create or formulate an RU using, let's say, a number less than 26 frequency subcarriers. So the minimum number of subcarriers per RU is equal to 26. The idea behind the subchannelization, if I go with this option, then I can support up to 9 stations at the same time, because instead of assigning the whole channel to one client, I can assign each RU to a user. If we go with this option, then I can use, as we can see here, we can bond these two into one bigger RU. So I can use 1, 2, 3, 4, 4 stations, plus the one in the middle can be used for another station, so a total of 5 stations. Also, if I double this, or sorry, bond these together, I can come up with a bigger RU that I can assign. So a total of 1, 2, and this can be used for a third station. So a total of 3 STAs. If I assign the whole subcarriers or the bigger RU within the channel, then I can assign it to one STA, and this actually represents the normal pre-11AX channel assignment to one station at a time. Okay, I can also mix and match, let's say, RUs together. So maybe I can go with this option. So maybe I can assign this to a user, this to a user, and I can bond this into something like this with 52 subcarriers and assign it to a user. Also, I can assign the remaining chunk as whole to another user. But who decides which user gets which frequency or which RUs? This one is a function of AP scheduler. AP scheduler. It's very important function. Actually, Wi-Fi vendors can be, let's say, tested or verified, or you can actually perform a comparison if you want to go with vendor X or vendor Y based on the efficiency of the access point scheduler in taking the decision of let's say RU assignments per user. Because for example, I can assign a user who has a 4K video a bigger RU, whereas I can assign smaller RUs to stations that transmit smaller frames such as voice frames. So we already know that the decision have to be taken in 11AX on per frame basis. So that put huge burden on AP scheduler to decide per frame which RUs to assign to which user in a multi-user transmission. Anyhow, let's leave this and we will discuss about this later in this series. Okay, good. So let's clear things for now. And we have a question. Let me show it here. So basically, the question says, in previous 82.11 standards such as 11AC or 11N, we used to use channel bonding in order to achieve higher data rates. Now in 11AX, we are, let's say, doing the reverse operation. So we subdivide the channel in order to assign those subchannels to RU. So how come that enhance 82.11 AX operation in general? Well, now, as we have discussed initially, 11AX was introduced not to increase throughput, but actually it was mainly standardized in order to enhance the efficiency. So let's say the researchers cared about efficiency in the first place. So if that item that they tried to make it more efficient brought, let's say, better throughput, then that's good. But their main target was to enhance the efficiency. So if you remember the case where we have one access point, let me grab another color. So this is an AP, and we have 4 clients, 1, 2, 3, 4. If one client is transmitting, the others are waiting for their turns in the waiting list. So instead of having them to wait, I can subdivide the channel. And for example, I can take this option, okay, here, and assign these 4 RUs to the 4 clients. And by that, I can, let's say, cut down the waiting time that each station has to wait and allow them to transmit concurrently. So the whole idea about this enhancement is written here. Let's read it together. So the transmission over RUs not only cut down the excessive overhead at the MAC layer, but it also minimized contention. You see, in our case, we allowed all 4 stations to transmit at the same time. So they don't have to wait or they don't have to contend to access the medium. The situation would be, let's say, noticeable if I have 40 devices. If I have 40 devices and one client is assigned to the whole channel, okay, then 39 would be waiting. So maybe I can use, let's say, 40 megahertz channel, and we said with 20 megahertz channel I can support 9 concurrent users. If I use 40 megahertz channel, then this number would be doubled, so 18 concurrent users can be served at the same time. So this would cut down the contention and the overhead at the MAC layer. And this is an extreme enhancement that 11AX introduces to enhance the efficiency. So that's it for this part. I hope you find it useful. Let us stop here and we'll see you in the next section. Thank you for watching.